Hello and welcome. My name is Marcel Nicolaus. I'm a sea ice physicist at the Alfred Wegener Institute here in Bremerhaven. My research interest is mostly the radiation budget of snow and sea ice in the Arctic, but also in the Antarctic. I'm working with a remotely operated vehicle under the ice and with autonomous stations drifting around on and in the ice. In MOSAiC, I'm involved since the very beginning, so almost 10 years now, and I'm leading the ice team. My personal questions here is, how do snow and sea ice make it through the seasons? From the winter through the spring, all the way into the summer, when they might leave the Arctic landscape full of melt ponds and even melting away. And with these observations, what are the processes behind it? How do these processes interact today, and how might that change in future? When I talk about sea ice, or when many people talk about sea ice or the pack ice, often the snow is not really considered. Although the snow rules. The snow rules many of the processes that we study and usually connect them to sea ice. Snow has more extreme physical properties. The thermal insulation is stronger. The optical properties, let's think about the albedo, dominate the pack ice properties. All the surface properties, the melt ponds in summer come up, and everything that we see from airborne or satellite missions first sees the surface, first sees the snow. And obviously snow itself has a mass, but it also, through its other properties, strongly controls the sea ice mass balance. And as a freshwater medium, it's unique in that system. That's why when we talk about sea ice research, we should always extend it to snow and sea ice research, which we do explicitly here in MOSAiC. Sea ice and snow are the central elements of the Arctic climate system, not only because they sit between the atmosphere and the ocean, but in particular because they integrate the fluxes, big fluxes from the atmosphere and for the ocean, and in between, small differences have huge impacts for the snow and the ice cover. When we study the sea ice, we are in strong interaction with the atmosphere team for all the fluxes and exchange processes at the surface, and with the ocean team with all the exchange processes at the bottom. The biogeochemical work strongly focuses on the exchange of gases and particles with the ice and through the ice. And we are best friends of the ecosystem because we study the habitat, because sea ice is a habitat not only on the surface, in particular in the ice and under the ice for small microorganisms and algae. And for MOSAiC, the sea ice is also of a particular interest because this determines many things of our project. This is what the main flow is made of. It's sea ice and snow, and the sea ice and the snow will also then, in the end, control the drift track of the entire project. When we talk about sea ice and Arctic and climate change, everybody has heard about shrinking sea ice. Yes, that's right. The sea ice is getting less. It's getting less extended, it's getting thinner, so the volume changes and the extent. But beyond that, and that's probably as important, it gets younger. The times of the big and multi-year pack ice regions in the Arctic are over in most areas, and it's only a small region that still has it. It's becoming increasingly dynamic, this younger and thinner ice, and with that the transpolar drift changes. And as a consequence, all the interactions in the Arctic between the atmosphere, the ice and the ocean change, and also the interactions between the physics, the ecosystem and the BGC processes change over time. Knowing about all these changes, we can easily identify the needs that we have for MOSAiC. We certainly need to better quantify and understand these processes with all these linkages. We have to bridge the scales from the microorganisms to the Arctic basin because there are impacts on all these scales. And finally, we will improve our forecasts, but not only for the snow and ice cover, but for the entire Arctic climate system. A lot of our scientific work is not only related to the measurements we are doing now, but also already for planning of the experiment, because the ice will determine the drift. So we worked a lot on retracking ice drift of the last years to find the perfect or the optimal starting position. It was a lot of scientific support and planning needed to plan the ice camp and the area around it with the distributed network. We were studying the genesis of the sea ice before it now became our ice flow. So what is the history of that ice? Where did it form? Where did it come from? And all this is the basis in the end now for the experiment ongoing. And in addition, here at home, we have additional possibilities through satellite remote sensing data and through drift forecasts to support the teams in the field to help their decisions, and with that also to understand the system a little better. So what's so particular about the ice work in MOSAiC? What do we want to achieve? First of all, it is the big time series. have a consistent data set of all our key parameters for 1 year, being consistent in the method and also in the data handling. But we also have to focus on the new aspects compared to all other studies. So, timely focus, the snow on sea ice, to bridge between the different scales, or to focus more on interdisciplinary work instead of having multiple expeditions going in parallel or one after the other. There are many of the first things in MOSAiC, but being the first is not necessarily unique, but to connect all these first things into a unique project, that's what we are aiming for here. For example, if we talk about the links between the field observations and the models, we do not want to generate a data set that might be used someday somewhere in a model, but we want to have that direct immediate interaction already now, and we started to implement that. And in the end, the ice work is only one small MOSAiC piece in that big climate study. When we talk about key parameters, what are our snow and sea ice parameters? For the snow, it's obviously the thickness, the mass and distribution. So the simple question, how much snow is there and where is it and when is it there? And if we look into the snowpack, what is the stratigraphy? What are the properties of all these layers? And what, in particular, what is the property of the surface? Because that determines the albedo, the roughness, and that's seen from all the satellites. In the sea ice, again, the question is, how much ice is there? But then, looking into the ice, also the stratigraphy, the ice properties, what lives in the ice, what are the optical properties of the ice in summer? How does the entire ice pack move later and through the year through the Arctic? And what flow sizes, for example, are there? Is it many small, one big one? And how does that affect the surface and the bottom topography of the ice pack? In summer, melt ponds might be before ice or snow, but they are most characteristic and a key topic of the ice team. And with all that, we have the connections to the atmosphere and the ocean, and with that to these teams that study these spheres in more detail. In addition to having this unique time series of all the parameters, we have different foci in different seasons. Obviously, solar radiation fluxes don't play a role in winter, but therefore in the beginning of the experiment, the thin ice, the young ice, the very dynamic ice has its own challenges, and we want to study the dynamics now in the first legs in particular. In spring, the sun comes back, the snow plays a big role, but at the same time, leads and ridges will shape the landscape beyond the original formation of the ice. And then obviously the big summer topic is melt. What do sea ice and snow leave in terms of melt ponds, and how much of the ice makes it through summer, and how would the refreezing look like in autumn again? All our time series and also the seasonal foci, they're interrupted by what we call events. Events in the ice team and for most other teams are in particular storms, leads and ridges. Because if a storm passes by the main ice camp area, it probably has very different effects depending on the season when it happens. When a storm comes, it changes the snow accumulation, it moves the ice around, it will exactly form, or often at least, form these leads and ridges. But what happens to a lead or ridge in the different seasons will be very different. In winter, a lead rapidly refreezes and forms new ice. In summer, it might support the breakup of the ice. In winter, the ridge piles up. In summer, the deformation event might also just help to deteriorate a ridge and let all the ice blocks fall into the sea. So events have to be planned in, but we never know exactly when they might appear. Depending on who you ask in our ice team, the scales are very different. Some are really interested in the very small in-ice microstructures, and others look with satellites onto the ice landscape and wonder how important that is. But in the end, and that makes MOSAiC again unique, we have them all on board. We have people that dig into the snow, into the ice on the millimeter scale or even beyond, and we have people that operate the biggest zoo of remote sensing operation sensors on the ice. And in between, we do transect over the ice to understand our flow better. We do dives with the ROV system under the ice to map the ocean-ice interface. We fly with helicopters and drones over our ice camp and connect to the distributed network in the tens of kilometers around. But we also have a big spring airborne campaign that flies aircraft all the way from the land, from the Arctic shore, to our ice camp. As of today, we are already 4 months into the experiment, and leg 1 and leg 2 are mostly completed. So what did these first 2 legs give us? First of all, we established the ice camp. If we look to the map, every single dot, every square on this map stands for one measurement, for one deployment, for one project. And they are all somehow connected. So we were successful in establishing this camp, and now we want to maintain and extend it over the next legs. So we have not only set it up, but we also measured the first 4 months of data. So we have 4 months of Arctic winter data of all our key parameters, consistently measured as planned before. But we also experienced strong ice dynamics. If we look, for example, to these radar images here, we can see a 7.5 by 7.5 kilometer footprint of radar, with smooth areas in gray and the bright areas are ridges and deformations. And we can see how around the ship that ice moves, piles up ridges, relocates and comes back again. We experienced the first storms and ridge events, and we now have an idea how these look in winter, and we are curious to see how they look in spring and summer. And for example, we were able to obtain a 3D image of our flow, mapping with an ROV from underneath, mapping with a laser scanner from the surface, and if we repeat that a couple of times through the year, we'll also see how all this icescape and landscapes changes in 3D. To sum it all up, what will the ice work in MOSAiC result in? First of all, we will get that unique data set, time series, a data set for generations. It is the time series, it is the most comprehensive and best planned time series that we have, and there's nothing comparable. Based on that, even after we left the ship, we'll work on this data set for decades, and we'll have to continue then the collaboration in order to provide new insights into the processes, to bridge the scales across the Arctic and across all disciplines. And then, with that, we will elevate our understanding of the Arctic climate system and finally also improve our predicting capabilities. And last but not least, thank you for your attention and your interest in our work. I'll be happy if you would like to join more of our work through all the channels that you might know.